Hi, everybody. I'm Justin Richer, and I'm the CTO of UberEther. Today, I'm going to be talking about a new specification that's come out of the IETF in the last year, and that's HTTP message signatures. This is RFC number 9421, and this was just published last February, so about a year ago. Now, this specification allows you to add a cryptographic signature to an HTTP message, and that guarantees some forms of security in transit. But you might be asking yourself, why would we need to do this? Don't we have TLS? Don't we have HTTPS and all of this other stuff to give us security? Well, this is a specification that allows you to add a signature to the HTTP message itself and not the conduit that it transits on. Now, there's a lot of reasons that I might want to do something like that. I want to make sure that the sender is the sender that I intend. I want to be able to protect it across multiple hops. And that turns out to be a really hard thing to do with HTTP, because HTTP messages have a way of changing in transit. So the thing that I send, it doesn't look like the thing that gets received. I may have a perfectly reasonable message that I think that I understand. I know where all the bits go, the order of all the headers and everything like that. And then it's going to hit an intermediary. That might be a reverse proxy. That might be some type of termination endpoint. And then it's going to come out the other side looking pretty different. And even though under the hood it's the same message, the fact that it is looking different to the receiver is a huge problem. Because it turns out the whole point of a cryptographic signing mechanism is that even if a little bit of the underlying message changes, you invalidate the signature. So how on earth are we supposed to deal with this thing that we know that once we send it out into the world, it's going to change on us? Well, the first thing you might be thinking is that since this thing changes, what if we wrap it in something that doesn't change? What if we take this out of the HTTP world and sort of put it into a little bucket on its own and wrap all of the important bits inside there so that we can actually send it across the wire and it doesn't get messed with? So it turns out that people have tried this. Way back in 1999, the SHTTP protocol was proposed by the IETF. Now this is not HTTPS that you might be familiar with. This is SHTTP. And this encapsulates the message and inside of one HTTP transaction into another. And there have been a few attempts at doing this type of encapsulation, and sometimes it works pretty okay, like we have with the DPoP signatures that OAuth uses these days. But for the most part, there are some pretty hard limits to encapsulation. First, anything that you need to sign needs to be inside the encapsulated envelope. So for example, if you want to sign the method, you have to copy it in there somehow, and then carry that copy across the wire with you to the other side so that it can be verified. This type of thing leads to some sneaky security problems, because if I get that message on the far side, and let's say I'm looking inside this signed body and it says that it's a post, and the signature validates and all of that's good, but the message that came in got changed to a GET from a post somewhere along the way. Now normally, I would want that to be an invalid signature. But the thing is, because I did this encapsulation, the encapsulated portion works just fine. And the portion that's outside that, the actual HTTP message, that's where things get changed. So which part do I listen to? And you could end up taking this to the extreme and going down the road of something like SOAP, where you end up ignoring all of the good parts of the HTTP protocol stack and just putting everything inside of a body that gets signed on its own, and that's where all of your important semantics are. And I've been around long enough to know that that approach really doesn't work well with developers. That's why we saw the rise of things like REST and Graph APIs above things like SOAP. So what if instead we tried to have a detached signature? Now this would be a signature that gets carried alongside the message, but isn't actually wrapped up inside all of the stuff that it's signing. So how would we do something like that? Well, it turns out a few people have tried. And these attempts go back a long way. Some of these are in massive production, especially AWS signatures. And I have to admit, I'm responsible for a couple of these myself. The ones that were proposed to the OAuth working group almost a decade ago, and the stuff that just got published in the GNAP protocol last year. So all of these have existed for quite some time. So why would we go about trying to make a new RFC if we already had these solutions? Well, it turns out that all of these have holes in them and weird corner cases, and we wanted to really get to the bottom of that. What would make it different this time, though? The real answer is the HTTP working group. This is where this work was done, and that's really important. Previous work had been done in security groups like OAuth, or as community papers, or as part of vendor solutions. We wanted to bring this work specifically to the HTTP working group because, as it turns out, it's the HTTP parts of this that are really hard. That's where all the tricky bits are. And once you get the HTTP stuff to behave, well, then you can actually get the crypto bits to work pretty well. The real key here is that this protocol creates a common base string to work from, something that can be derived from the thing that we sign and the thing that's received. And this is the real key difference from other attempts that have gone before. So let's go through an example. This is a pretty basic HTTP message. It's a post. It's got a couple of headers in it. So first thing we got to do is figure out what parts of these that we're going to sign. Thing is, because this is a detached signature, we don't have to sign the whole thing. So if there's a header that we think is going to change or we don't care about for our application, we don't include it. If there's stuff that's really important to us, like for the example here, the method, then we do include it. And then we basically take that list, we decide an order, and we put all of that together. So once we have that, we take that message and we derive what's called the signature base string, and that's the thing that we can sign. We take each of the items in our list of things to sign, and through a deterministic process, we create this string that we can apply cryptographic primitives to. Now, this is not something that we send across the wire. This is just used to create the signature. And each of the items in here you see can be pulled pretty easily from that HTTP message we were looking at a moment ago. Once we have this, we've got a set of bytes. And once you have a set of bytes, it's pretty easy to apply a signing function to that. Now compare this to an HTTP message. I might not know the exact set of bytes at the time that I'm signing it. It could be going out through a proxy, or it could even just be going through an HTTP library that's going to add its own headers, that's going to reorder things. It could do all sorts of transformations that changes the bytes that go out on the wire before the other end sees it. But now, since I'm the one doing the signing, I determine what those bytes are, and I create the signature based on that. From there, I can add those to the message itself. And the result is a pair of headers. One header, signature input, tells the other side what are the things that I signed, what are the order that I signed them in. And the next bit is simply just the signature itself. So you might be asking yourself, why do we have two headers? This seems like it's a little bit too complicated. Well, the thing is, HTTP message signatures is designed around a wide variety of applications, including ones that require or allow multiple signatures to be applied to a message at the same time. So if you're going through a proxy, for example, you might want to add a signature at the proxy before it gets passed along to the next stage. Also, we wanted to use something called HTTP structured fields. This is a way to put data structures that are non-recursive and very well defined into HTTP headers in a way that's native to the HTTP world, unlike something like JSON, which would need to be encoded or armored before it's passed along. So now we have this message, and we want to send it out across the internet. Now, the funny thing is, once we send that, weird things can happen to it like we've been talking about. Who knows what kinds of dragons and mythological creatures are going to chew on this message by the time the verifier actually sees it. All of the bytes that we sent out are probably not going to match the bytes that the verifier sees. And since we're dealing with a cryptographic signing protocol, that signature is going to fail because the bytes are going to be different, even if it's semantically similar. See, this signed request is not the same as the one that went out. There's a bunch of differences here. So the headers got reordered, for example, a new header got added, even the date header, that content got changed. So the signature, if I were to apply it on just the set of bytes that got sent out, that would fail. So how do we deal with this? Well, the first thing we do is we look at that signature input and we pull that data out of the message. This tells us, you'll remember, not only what was signed, but the order in which it was signed. Now, the first thing that we need to do with that is figure out if the stuff that was signed matches my application. Because if my application really needs the method to be signed and that method wasn't signed on the way out, well, then I can't use the signature no matter if it validates or not, because it doesn't match the semantics of my application. The next thing I do is I rederive the signature base. So I take that new message that I received, even though the headers are in a different order, even though things might have been combined, even though things might have been reformatted in some places, I can derive the exact same signature base string from that new message. This allows me to create the same set of bytes, which I can then apply my cryptographic functions to. This helps me verify that the message signature is valid over all of the parts of the message that I actually care about, and that could change between different applications. Some applications might need to always sign the method. Some applications might know that the method changes at the proxy, and so they never sign that. Or that information is not semantically relevant to the thing that they're trying to prove. So the message signature specification doesn't actually specify a core list of things that you have to sign. What it does, though, is it gives you a toolbox that allows you to build a secure application based on this as one of the elements. This also lets us do some pretty neat tricks. So for example, anytime you get an HTTP response, that response is in response to a specific request. Well, the person signing the response, they have access to that request because they're responding to it. And so we can include things in the signature that were part of the request message that don't get sent across the wire again. They are not part of the response directly, but they were part of the context that created the response. Now, when the party that's verifying this gets this message, how are they supposed to look up what was in the request? Well, ostensibly, they were the ones that sent the request, so they should have enough information to be able to recreate the signature base string based on that. We can also sign the message content, albeit a little bit indirectly. We can use a family of digest headers to create a cryptographic hash of the message content and attach that as a header to the message. Once it's a header, we can apply the signature to that just like we do any other header. Now in this case, we have another verification step that we need to do. We need to make sure that the hash of the content that's in the header actually matches the hash of the content that was sent in the message. If we don't do that, we run the risk of actually accepting content that doesn't match the signature because it's an indirect coverage. Another thing that we can do is sign a TLS certificate in the same way. Now, if I hit a TLS terminating reverse proxy at some point along the journey, it's going to strip the TLS message off of that. And even if I'm doing mutual TLS between endpoints, that only happens between those two hops. So how does a downstream application process it? Well, we can use the client certificate header field to wrap that signature into the message and send it down. Well, since I'm doing that, I might as well have the terminating proxy sign that header and declare that this really was the configuration state of this message before it was passed on. We also have the capability to have multiple signatures inside of a single message. So if I get a message at any point in my application, maybe I'm in a proxy or maybe I'm just at another stack of the application, if that message is already signed, there's no problem with me adding additional signatures to that. I can choose to sign the same things. I can choose to sign different things. I might be using a different key or a different application tag. None of that matters because the message can carry both side by side. Now you might here be thinking that it makes a lot of sense that if I can have multiple signatures and I'm a proxy and I get a signed message, wouldn't it make sense for me to just sign the signature and pass that along? Well, it turns out that this is a problem. And we worked with some cryptographic researchers who submitted their findings to the IETF and pointed out exactly how something like this could be exploited. So in the specification, there is specific guidance that says why not to do this and what to do instead. And this type of collaboration is one of the hallmarks of working in an open standards world. So this works really well for a whole lot of different HTTP applications, and it's being deployed in a bunch of different places today. But a lot of stuff that I've worked on over the years has dealt with the OAuth family of protocols. So how does this apply to the world of OAuth? There's a bunch of things that we could do that could apply this to the OAuth space. After all, an OAuth secured message is really just taking a message, adding a new header to it with the access token, and then once that header is in place, we can sign it like anything else. So our OAuth protected request has this additional header. So we add that header into the signature base string and configure our application so that it always requires that authorization header be covered under the signature. So we sign that message and include that in the signature base string just like we would anything else. Really, there's nothing special here. It's just a header and we can include it under the signature. But we can do some interesting stuff to this because the presentation is now tied to this specific HTTP request message. We've tied the method, the authority, and the path, and the authorization header all together with this signature mechanism. We've also got replay protection built in. We can have a created timestamp, and we can have a nonce built into it, and we can tag this that this is an OAuth protected resource. This is us specifically trying to sign the OAuth request. But it's not just about using it with tokens. There's a lot of other ways that this specification could be used in practice. So for example, we could use it for proof of possession of client keys. We could use it for signing client attestations. We could even use it in server responses. So when you get the token response back, in addition to it being over TLS, you can have an additional signature that says that this really is the message and the content of this message. We can even do some neat tricks with signing things like introspection responses. Now, something very interesting about introspection responses is that they are always tied to a specific token request. And as we talked about before, HTTP message signatures gives us a way to tie a part of a request into a signed response. And there are a lot of other ways that this could be used. For example, signing browser cookies, or tying things to assertions, or passing things across a distributed network. There's a lot of possibility here. I want to encourage everybody to go check out httpsig.org. It's a free resource that we've provided to the community that allows you to test out HTTP message signatures. You can paste in an HTTP message, look at the process of how the signature is built up, and then sign it and get the results. This is actually functioning. And on this page, there's also a ton of information about libraries and links to the specification itself so that you can go use this and apply this in your own applications. HTTP message signatures are a very powerful security component, but the real power comes in how this gets applied to your applications. So how are you going to use it?